Hi, my name is Bart Polson, and in this tutorial I'm going to show how to calculate a multiple regression in SPSS, now known as PASW for Predictive Analytics Software. I'm using version 17, but the previous versions are essentially identical for what I'm doing. I'm also doing this on my Mac, but the Windows version, again, is essentially identical. Multiple regression is used to predict the values on a quantitative outcome variable using several other predictor variables. They can be quantitative or categorical, so on. I'm using a data set that exists in SPSS that's called world95.sav. The .sav is the suffix for a SPSS data set. You can get it by opening up the data sets and going to the end to this one, world.sav95. I have it open already. And it's data for 109 countries from Afghanistan to Zambia, and there's the US. And it has information about population, life expectancy, literacy, predominant religions, and so on. What I'm going to be doing in this one is I'm going to be taking a few variables to predict women's average life expectancy for each one of these countries. Now, in a previous one, I showed how to calculate a correlation matrix, and that's important because the same information is used in calculating a multiple regression. In fact, I've kept the results from that one, so let me show them right here. Okay, what I have here are 5 variables. I'm going to use this one, average female life expectancy, as my outcome. And then I'm going to use these, the literacy rate, the GDP, the daily caloric intake, and the birth rate as predictor variables of female life expectancy. This matrix has the variables listed down the side, has the same variables across the top. It's symmetrical on the diagonal. The ones right here are each variable correlated with themselves, so that's going to be one. And you see, for instance, that the minus 862 here is minus 862 here. Now, one important thing to note about this is all of the correlation coefficients are very strong, and they are all statistically significant. You see the asterisks right there. That has to do with this one, the significance. It says sig two-tailed. This is the probability level from a null hypothesis test, and all of them, it's extremely small. It's less than 0.001. So please remember, they are all statistically significant and all much less than 0.001. Because what I'm going to do now is I'm going to use a multiple regression to look at the association of all 4 of these together to predict life expectancy for women. So the way I'm going to do this is I come up to Analyze and down to Regression. I'm going to use linear. I used this command for a bivariate or simple regression earlier. Now we're just going to get a little more sophisticated. Now, I already put the variables in there from an earlier one, but what I did is I came over here and I just selected each of the variables, pressing them in here. I have average female life expectancy, literacy rate, GDP, caloric intake, and birth rate per 1,000 people. Now, multiple regression can be a very complicated and very sophisticated thing. There's an awful lot of decisions to make that can make a big difference in how things work. However, for this one, I'm going to use the simplest possible version where I simply keep all of the defaults the way they are, and this is not a bad method for most regressions. So I'm just going to come down here and I'm going to hit OK. Now this one right here is what's called a syntax. It's a command, a written command for what I just did. Nice thing is you can save that in a separate file, you can run it again later, you can modify it. I may talk about that later. This says that I did a regression. This one says which data set I used. See, it says world95 right here. This says what variables I used as the predictor. Here, birth rate, GDP, caloric intake, and people who read. And that this one is the outcome variable, the dependent variable, which is average female life expectancy for each of the 109 countries. This one right here tells me that they are very highly correlated, that these variables predict life expectancy very well. This first one here, the capital R, is called the multiple correlation coefficient because it's looking at the association of all of the variables together. The maximum value is 1, positive or negative. This has a 0.912, which is extremely high. More frequently, people use the R squared, which is, 912 squared is 832, which means that 83% of the variance in average life expectancy can be predicted by the combination of these four variables. Now this one, adjusted R-squared, takes into consideration the number of observations and the number of predictor variables to make sure that things aren't too inflated, so it's generally smaller. The standard error of the estimate is simply something that goes into the hypothesis test for this one. We're not going to worry about that. This next one is also an indication of how well the model fits. All you need to know is that it fits really well. The significance test right here is much, much less than 0.5, which means a 5% type 1 error rate or a 5% false positive rate. This is a very tight model. This is a good one. The important ones are down here under where it says coefficients. Now, what we're going to look at is, for instance, this one right here, the constant, that says when all of the predictor variables are 0, which actually isn't possible, you would start with an average life expectancy for women of 43.778 years. And that this number is significantly different from 0, and there's no shock right there. The more interesting ones are these correlations right here. This says for the percent of people who read, for every percentage point of people who read, add 0.226 years to the average life expectancy for women. This one, GDP, says add 0. Caloric intake is add 0.006. Now that means for each additional calorie, which is why this is a very small number, because calories, you have thousands of them. And then birth rate is negative. Now, on the other hand, if you come over here to the sig column, that means the probability level for each one of these. And again, they generally need to be less than 0.5 to be considered significant or meaningful or reliable. All of them are less than 0.5, except for this one right here, the 786 for the GDP. Now, here's the important lesson about multiple regression. Let's go back up to the correlation matrix I showed at the beginning. When you look right here, this is the outcome variable, average female life expectancy. Every one of these variables, including GDP, are highly correlated on their own with the outcome variable. Please note, GDP has a correlation of 642, which is really big, and has a probability level less than 0.001. All of them do. But when we come back down here, GDP is no longer significantly associated. Now, the reason for that is because multiple regression looks at the combination of these four variables to predict the outcome. This is the contribution of each variable, but only in combination with each other. And that's one of the reasons why you might want to look at both the individual or bivariate correlations, which I did above, and these ones down here. However, it should be noted also that this is a much better prediction than any of the ones individually up here. The highest correlation we have here is 865 and then 862, which are very close down there. The entire model together has a multiple correlation of 0.912. So it's not a huge improvement, but it is still there. And so it might be better to use the entire model to try to predict women's average life expectancy. Now, the fact also that the literacy rate and the daily caloric intake are both positively associated and the birth rate is negatively associated with life expectancy, again, may have more to do with the economic development and health care available in countries more than anything else. But that's what we need to know about multiple regression for right now. Thanks.